Welcome to this explainer on water quality testing. Today, we're uncovering the unseen dangers lurking in our water and breaking down the exact scientific methods used by experts to detect them. It's incredibly easy to take the water flowing from our taps for granted, but as we'll see, true water safety goes far beyond what meets the eye. Here is our roadmap for today. We're going to look at the invisible water threat, key water quality indicators, tracking bacterial contamination, home strips versus lab tests, and finally, decoding your water report. Let's get right into it. Section 1. The invisible water threat. Trusting more than your senses. It's so tempting to just trust our eyes and taste buds, right? If it looks crystal clear and doesn't smell like a swimming pool, we assume we're good to go. But the most nefarious contaminants are undetectable by our five senses. That quote right there hits the nail on the head. Relying on a quick sensory check is literally the worst way to evaluate if your water is safe to drink. Clear water absolutely does not guarantee safe water. Instead of trusting our eyes, comprehensive testing hunts down three main categories of invisible contaminants. First up, we have bacteria and viruses. These are pathogens that usually sneak into the water supply through sewage leaks or agricultural runoff. Next, we've got chemicals. Think pesticides, herbicides, and volatile organic compounds, or VOCs. And finally, heavy metals like lead and arsenic, which can leach straight into your water from old, outdated plumbing or industrial waste. Any of these can trigger severe health risks, ranging from sudden stomach bugs to chronic long-term diseases. Moving on to Section 2, Key Water Quality Indicators, the what we look for. What's actually super fascinating here is that scientists and water treatment facilities don't usually test for every single individual chemical right out of the gate. That would take forever. Instead, they look for general indicators that act as massive red flags. First up is turbidity, which is basically a measure of water clarity based on suspended particles. It's measured using a nepilometer in units called NTU. Now, if turbidity hits over 5 NTU, the water isn't just visually unappealing. Those suspended particles actually act like a physical shield, protecting harmful pathogens from the entire disinfection process. It's literally armor for germs. Another absolutely vital indicator is total dissolved solids, or TDS. This essentially tells you how much stuff, things like calcium, sodium, iron, or manganese, is mixed into your water. It's measured in milligrams per liter, and a high TDS level can give your water a really weird, salty, or bitter taste. Plus, those high dissolved solids are highly likely to leave behind this scaly mineral buildup on your pipes and household devices, effectively destroying your plumbing from the inside out. And of course, testing the pH level is a crucial baseline metric. The pH scale tells us how acidic or basic the water is, with the acceptable limit usually sitting right between 6.5 and 8.5. If your water is highly acidic, so a low pH, it's going to pit and corrode your pipes. Worse, it can leach toxic heavy metals like lead straight into your drinking glass, which often gives it a metallic taste. On the flip side, highly alkaline water will have an oddly slippery feel, taste a bit like soda, and leave extensive scaly deposits everywhere. Which builds right into our third section, tracking bacterial contamination. The microbe matrix. Take a look at this. It perfectly illustrates the hierarchy of coliform bacteria. Now, coliforms naturally hang out in soil, surface water, and the digestive tracts of animals. On their own, many of them won't actually make you sick. But testing for broad total coliforms acts as an incredibly effective early warning system. Why? Because they sneak into your water the exact same way that the really dangerous pathogens do, like from a sewage leak. If you spot total coliforms, you drill down. You test for fecal coliforms, then E. coli, and finally, the highly dangerous pathogenic E. coli. And just for the record, the World Health Organization mandates that pathogenic E. coli must be at absolute zero in safe drinking water. Zero. To actually track these bacteria down, laboratories use two main testing methods. First, basic presence/absence tests. These give you a simple yes or no result, and they are fantastic for treated drinking water where you fully expect a negative result anyway. But if you get a positive, you need a quantified test. Using statistical models like the most probable number, or MPN, or direct colony counting known as colony forming units, scientists calculate the exact concentration of the bacteria. This is absolutely critical for figuring out the actual magnitude of the health risk and deciding how to effectively treat that water source. All right, on to Section 4, home strips versus lab tests, methods ranked from worst to best. So the real trick is knowing exactly which testing tools to use in order to find these indicators and bacteria effectively. Ranking the methods from worst to best, we start at number 1, sensory evaluation. Just relying on our terribly flawed human senses. Number 2, DIY methods, like testing water hardness with soap, which completely lacks any real accuracy. Number 3 brings us to handheld digital instruments. These are great for an immediate pH or TDS reading, but they're limited to only a couple of parameters. Number 4 introduces DIY test strips, getting warmer. And finally, number 5, state-certified mail-to-lab testing, the absolute gold standard for analyzing your water. Let's zoom in on those top 2 consumer options. DIY test strips are incredibly affordable at under $50, and they give you instant results for basic stuff like pH and chlorine. But honestly, their accuracy is pretty low and heavily relies on visual interpretation. They simply can't match the comprehensive scope and high precision of a mail-to-lab kit. Sure, lab testing takes 3 to 10 days and is more expensive, but it utilizes advanced mass spectrometry and chromatography. They test for complex, dangerous contaminants like PFS forever chemicals, VOCs, and heavy metals. If you are making definitive health and safety decisions for your family, lab testing is for sure the only way to go. Finally, let's look at Section 5, decoding your water report. From data to action. Okay, so you've sent your sample to a certified lab, keeping it cold on ice packs to preserve the sample's integrity, of course. And eventually, you receive this detailed analysis report back. You need to know how to interpret that data. You're going to frequently see your contaminant results measured in milligrams per liter. It's really important to know that 1 milligram per liter is exactly mathematically equal to 1 part per million, or ppm. And for the extremely toxic substances, you might even see parts per billion, or ppb. To help wrap your head around just how insanely sensitive these state-certified laboratory tests are, consider this. 1 part per million is equivalent to dissolving a mere 0.03 of a teaspoon of sugar into a fully drawn bathtub. That is a tiny amount. And the crazy part? For some toxic chemicals, the safety threshold is much, much lower than that. So what do you do with this data? Well, if your lab report actually detects harmful levels of contaminants, your action plan should be step by step. First, compare your results to local environmental standards. Next, get on the phone with your local health department. They're literally there to help you understand what the results mean based on your regional geology and agriculture. If harmful germs showed up, switch to bottled water temporarily, right away. Then you can start looking into installing targeted filtration systems, like reverse osmosis, to tackle your specific contaminants. Oh, and a quick reminder, if you're a private well owner, the CDC strongly recommends testing your water at least once every single year, because groundwater quality can change rapidly. We've seen today that the most dangerous threats to our water supply, from pathogenic E. coli to dissolved heavy metals, are entirely invisible to the naked eye. We've explored the entire toolkit, from basic indicators all the way to high-tech lab analysis that pulls back the curtain on these microscopic hazards. So, armed with this new understanding of what really makes water safe, I want to leave you with one absolutely crucial question to ponder the next time you turn on the faucet. Is your clear water actually safe to drink?